Welcome to our second class on electrochemistry. I want to remind you that a cell reaction, whenever a direct current passes through an electrolytic cell, oxidation and reduction take place at anode and cathode respectively, and at the anode oxidation takes place with a transfer of electrons from the reduced species to the electrode. At the cathode reduction takes place and electrons are transferred from the electrode to the oxidizing species. We have covered all this in the last class. Now, when the electric circuit is completed, ionic conduction occurs through the solution. So, this equation we have seen that the generalized redox equation in the last class, that A moles of R moles of A species A and S moles of species B get oxidized to P moles of oxidant A and Q moles of reductant B. Then we have written an equilibrium constant, and then we have written a thermodynamic constant, that is Q, which is essentially same as equilibrium constant, except the equilibrium terms are replaced by activity. And this activity is nothing but concentration into multiplied by its activity coefficient. Since both these are thermodynamic considerations, we get the free energy delta G should be corresponding to the difference between RT ln Q minus RT ln K, that where R is 8.316 joules per mole per degree. And then we have also shown that the free energy is also equivalent to number of electrons transferred and number of Faradays and the EMF of the cell, that is potential of the cell in volts. Then we can write comparing these two equations. This is delta G with respect to electrochemistry, and the previous slide delta G the thermodynamic quantities. Then we have combined these two and equated. Then we have written E cell is equal to RT minus RT by NF ln Q plus RT by NF ln K. Then we have separated the equilibrium and activity coefficients with respect to species A and species B. So, the E cell is actually given by the difference between the two, that is potential of the first cell B minus potential of the cell A, where the actual potential is given by E A is equal to E naught A minus RT by NF A reductant multiplied by number of moles, and that is the activity, that is this concentration term actually refers to activity. Similarly, we have written for B. Now, these equations where E A is equal to E naught A minus RT by NF ln A reductant by A oxidant moles of P at activity coefficient. Similarly, for these are known as Nernst equations. This we have covered in the last class. Now, for convenience, that means what actually we have done is we have written half cells. The half cells actually represent only one species, reaction occurring at one species. Only when the cells are connected together, they represent a complete cell. So, we have written A oxidant is equal plus n number of electrons is equal to A reductant. Similarly, half cell reaction, the other half cell, even though it is the electrons are accepted here, in the other cell it should be released here, but even though the electrons are released, we still write B ox plus Ne is equal to B reductant. That means, we have algebraically changed this equation to write oxidant at the left, electrons at the left and the reductant on the right side of the equation. This we can do for any of the half cell reactions. So, for convenience all the half cells are written as reductions, that means in this format. The overall reaction is obtained by the subtracting the bigger one, smaller one from the bigger one. So, the quantities E naught A and E naught B are called as standard electrode potentials for the half cell reactions, and they can be evaluated by setting a reaction in which one half cell the ratios of activities are unity and the logarithmic term becomes 0. So, no valid method has been discovered for setting up only a half cell of any reaction. It has to be coupled with another half cell where reduction or oxidation takes place. Therefore, it is necessary to choose an electrode to arbitrarily assign a 0 position on the scale of potentials. For this, we are using standard hydrogen electrode as a standard one by convention. It is not a scientifically chosen system, but for our convenience we have chosen standard hydrogen electrode as representing 0 voltage. So, what is standard hydrogen electrode? It is an electrode in which a hydrogen is dipped in a solution. The platinum wire is dipped in a solution containing hydrogen ions, and hydrogen is being bubbled through the solution at a partial pressure of 1 atmosphere over a platinized platinum foil in an aqueous solution in which the activity of hydrogen is unity. That means, concentration multiplied by activity coefficient. So, when the activity coefficient is 1, then concentration into 1 is activity basically. So, the activity should be 1. That means, the reference should be 0, that arbitrary value we have chosen. So, if the hydrogen ion SHE standard hydrogen electrode is showing 0 volt, others may be showing positive value compared to 0 and some may be showing a negative value. For example, if you take a look at this figure, I have written here, the figures are not very clear, but it is a standard reproduction from any of the textbooks. All what the title says is standard reduction potential at 25 degree centigrade. So, here you can see that somewhere in the middle you will see 0.00 here. So, 2 H plus 2 E going to H 2 and that shows 0. Above this, all the reactions are showing positive values. For example, here it is iron plus 2 electron going to Fe3, it shows plus 2.65 volts. It means, when an iron electrode is connected with the standard hydrogen electrode, it shows 2.65 volts. So, similarly, we have sulphate S2O8 plus 2E going to SO4, that shows 2.01. Then I am choosing an arbitrary random value, that is iodine here, plus 2 electrons going to 2I minus, that is iodide electrode, and that shows plus 0.51. So, tin here is another one, SN4 plus 2 electron going to stannous, that is shows 0.15. So, if you connect 2 hydrogen electrodes, what you would see is 0.00, that is the standard hydrogen electrode. After that, we have the values which are lower than that, that is chromium 3 plus electron going to chromium 2 plus, and that value is minus 0.41. So, H2AlO3 last one plus water with 3 electrons, it going to aluminum, and that shows minus 2.35. one conclusion you can draw from this is, so all the electrochemical reactions show either positive value with respect to standard hydrogen electrode or negative values with respect to standard hydrogen electrode. Now, the things which are showing positive values, they are all called as oxidizing agents, and the one compared with the negative values are called reducing agents. So, we can make further choice something like this. We can have a choice of common oxidizing agents, and here if I use potassium permanganate, its radical is MnO4 minus, oxidation state is +7, and when it oxidizes other systems, manganese reduces from MnO4 minus to Mn2 plus. That means, new oxidation state is +2 compared to +7. That means, the change in the decrease in the oxidation number is 5. That means, gain in electrons is 5. That means, it requires 5 electrons and for this reaction to proceed. So, this is a very strong oxidizing agent in our experience. Similarly, I can go for nitric acid. So, here it is +5 oxidation state, and then it is -1. So, +5 +4 and 1 electron. So, it can't be as strong an oxidizing agent as potassium permanganate. Like this, if you look at the oxidation potentials of the oxidants, you can make a list of which are the strong oxidizing agents. Similarly, you can compare the EMF with respect to hydrogen electrode and decide whether H2SO3 is a better reducing agent, stronger reducing agent, or oxalic acid. Obviously, you can have a choice of different chemical reactions which can be graded with respect to the oxidizing and reduction properties as compared to hydrogen. So, we have different kinds of electrodes now. Earlier I had described the standard hydrogen electrode is basically a solution of HCl of one unit activity, where hydrogen is being bubbled with a platinum wire fixed into the solution. Now, I can have different kinds of electrodes, not necessarily the gas and metal, etc. They are described as 3 types, belonging to 3 types: electrodes of the first kind, electrodes of the second kind, and then electrodes of the third kind. Let us look at what is first kind, electrodes of the first kind. So, it means a metal rod in equilibrium with its ions. That is the electrode of the first kind. I have given you 3 examples here: zinc metal, zinc solution with 2 oxidation state, it gains 2 electrons to give you zinc metal. That means, a zinc metal is dipped in a solution of zinc solution, Zn2 plus solutions, and that when it is connected with a standard hydrogen electrode, you would see an EMF of -0.763 volts. Another example is a copper electrode dissolved in copper electrode dipped in a copper solution, and the reaction would be Cu2 plus 2 electrons going to copper metal, that is reductant. Remember that all the metals are in the reduced state, their solutions are in the oxidized state. So, compared to if you connect this with hydrogen, you will get 0.337 volts. So, which is a better oxidizing agent among these two? This is minus, this is plus, and this would be a zinc would be a better reducing agent, because it is minus value compared to standard hydrogen electrode. This way we can get comparisons. So, similarly, I can have a silver wire dipped in a solution of silver nitrate, that is Ag plus, in the oxidized state. I am writing here at the bottom as a subscript. The reaction would be Ag plus plus E minus going to silver reductant, and the standard reduction potential is 0.0799 volts. So, like this we can have the reactions written, and the EMF of the potential is given by this expression. E A is equal to E naught A, that is standard electrode potential with respect to hydrogen electrode, plus R T by N F ln A oxidant, that is the actual EMF is standard electrode potential plus that modified by the oxidant and reductant ratio. Actually, there should be a reductant at the bottom here in this equation, ln A oxidant divided by ln A reductant, but reductant value is metal, and for metal activity is 1. So, we write A reductant, instead of writing A reductant we are writing 1. So, similarly, I can have a metal in equilibrium with a saturated solution. That means, I take a metal rod, dip it in a saturated solution of a slightly soluble salt. For example, I can take silver chloride. Silver chloride is very sparingly soluble. So, you make a solution in a beaker, take some water, add some amount of silver chloride, part of it will dissolve and remaining part will remain as a powder at the bottom of the electrode. That is a salt solution in equilibrium with its solution. In that, if I put a silver electrode, I have a half cell known as silver chloride plus electron. The reaction is represented by, it will pick up an electron and go to silver metal and release a chloride ion, and the standard electrode potential is 0.2221 volts. Similarly, I can choose other sparingly soluble salts like mercurous chloride Hg2Cl2 plus E minus going to 2Hg plus 2Cl minus. Here also a single electron is involved, and the E naught for this half cell reaction is given by 0.2676 with respect to standard hydrogen electrode. So, half cells of this type are widely used as reference electrodes. See, it is very difficult to have a platinum electrode with a solution of hydrogen chloride, gas bubbling, such a complicated reaction, and even to maintain or measure routinely, we do not need it is very difficult to maintain such electrode systems. Therefore, what we do is, since the silver electrode, just what I described, silver chloride in equilibrium with its own solution, does give reproducible results with respect to standard hydrogen electrode, and it gives you a value of 0.2221 volts. Now, that itself we can use it as a reference electrode instead of standard hydrogen electrode. So, I can choose silver chloride electrode as a reference electrode, and therefore, mercury chloride also I can use it as half cell and reference cell. Half cells of this type are widely used as reference electrodes, which are also known as secondary standards. So, instead of setting up a primary standard all the time with all its complications, it is better to use secondary standard. These are easy to fabricate and they are reproducible and they have very low temperature coefficient. That means, if the temperature varies, you would still you will not see much of the much change in the EMF, because they have a very low temperature coefficient. That means, temperature does not have a significant effect on the EMF. Now, we can look at the reactions of the silver chloride electrodes, that is Hg2Cl2, it can pick up 2 electrons and then it forms mercury metal and then plus 2 Cl minus. I can use saturated potassium chloride solution, and when you measure the EMF of this, it shows you 0.246 volts versus standard calomel electrode. So, if you this is known as standard calomel electrode, a mercury chloride solution, mercurous chloride solution in presence of standard KCl solution, that is saturated one. So, Hg2Cl2, if it is the same reaction can be represented, but it shows 0.280 versus standard hydrogen electrode. So, AgCl will show you 0.237 volts. So, all these reactions can be used as reference electrodes. Now, let us look at the third kind of electrodes we normally come across. This is nothing but two soluble species are there. That means, the oxidized state is also a solution and reduced state is also a solution. Earlier we had zinc as the reduced state and Zn2 plus, that is divalent zinc ions were in the oxidized state. Similarly, silver Ag plus Cl minus going to AgCl. In silver is the reduced species, that is a metal, and Ag plus is a solution. So, we have oxidized or reduced species in solution, oxidized species in solution and reduced species as the metal. Now, I am looking at systems in which the oxidized species is also a solution and reduced species is also a solution. Examples include ferric and ferrous. Ferric solution contains Fe3 plus and ferrous solutions contain Fe2 plus. So, Fe3 plus electron goes to Fe2 plus. Look at this reaction please, and you will see that ferric ion will pick up one electron to give you Fe2 plus. That means, when it picks up a negative charge, positive charge should go down by 1 unit and it gives you Fe2 plus, and E naught for this reaction when compared to a standard hydrogen electrode is 0.77 volts. Similarly, I can have 2 mercurous ions and 2 electrons going to Hg mercuric ion Hg2 plus, and this reaction is briefly referred as mercurous to mercuric. This is ferric to ferrous. Then I can have ceric to cerous, mercuric to mercurous, I have ferric to ferrous, ceric to cerous. On the left side I have the oxidized species, on the right side I have the reduced species in the same convention. And but the only difference is this Fe2 plus is in solution, Hg2 plus is in solution, Ce3 plus is in solution. That means, we do not have a metal electrode corresponding to either Fe3 plus or Fe2 plus, mercurous and mercuric, ceric and cerous. So, what are the electrodes? The electrodes are basically inert electrodes, something like platinum. They do not take part in the reaction. The only function of the electrode is to transport the electron to or from the ions in the solution. This is known as electrodes of the third kind. Now, I would like to summarize again: a metal ion in solution and equilibrium with a metal electrode, same metal ion, that is electrode of the first kind. Electrode of the second kind is a metal ion in equilibrium with its own solution, but the solution is saturated with respect to a salt. That is second kind. Third kind is oxidized species also in solution, reduced species is also in solution. I have two platinum electrodes dipping in ferric and ferrous solution, cerous solution, mercurous solution, etc. And the sign convention says that zinc 2 plus 2 E minus, this is how we are writing, it shows 0.763 volts, and a hydrogen electrode I am writing in the same way, H plus on the left side, electrons on the left side and reduced species on the right side, it shows 0.00 and Cu2, that is E naughts, and Cu2 plus 2 E minus going to Cu, that is minus 0.337 volts. So, one is a reducing agent, one is an oxidizing agent, and this is a neutral agent, that is 0. So, the E naught values are known as standard electrode potentials. Thus, if copper and zinc electrodes are constructed, each in contact with its own ions, copper is found to be positive and zinc is found to be negative, as observed in a voltmeter or a potentiometer. So, this is what the convention says, that you write the oxidized species on the left and reduced species on the right. Now, let us define a little some more terms with respect to electrochemistry, which you come across very regularly. One is reversibility. What is reversibility? A half cell, what we have written so far, is said to be reversible if a change in the direction of the current flow reverses the half reaction. That means, most of the half cells act reversibly in normal solutions, normal circumstances. Consider this zinc chloride system itself. The half cell, it says zinc goes to zinc 2 plus 2 electrons, and on the other side 2 electrons released from this zinc system will react with 2 AgCl to produce silver plus ions and zinc ions. So, if this cell is connected to a source at high source of electricity, to force the current to move in the reverse direction, the reaction will be the other way, that is the instead of current coming from zinc to silver, it will flow from say zinc to silver to zinc. So, all these reactions are reversible. That means, you change the polarity, current will go from positive to negative, and you change the polarity again, it will come back to this negative to positive. All you got to do is, it is a question of choosing the right way. So, if you want to coat zinc, coat silver on zinc, then what you should be doing is silver should be dissolving and then depositing on zinc. So, if you reverse the reaction, you can collect the zinc from the collect silver from the zinc electrode. So, the electroplating reactions are mostly based on this type of considerations. So, now look at this reaction, 2 H plus 2 E minus goes to H 2, 2 A G plus 2 Cl minus goes to 2 A G Cl plus 2 electrons. This is what happens in the silver chloride system, because there is some acid also, H plus goes to H 2. So, the overall reaction of this reaction would be, we just add these two and 2 electrons and 2 electrons will cancel. So, we write 2 Ag plus this reaction plus 2 Cl minus and 2 H plus goes to 2 AgCl and H2. Thus, it is seen that silver chloride electrode is reversible, but zinc half cell is not reversible. So, we can carry out this reaction only in one direction. So, not all reactions are reversible, but some reactions are reversible, some reactions are not reversible depending upon their thermodynamic properties. Now, another term I want to describe to you is polarization. An electrode is said to be polarized if its potential is at variance with the Nernst equation. This may be due to changes in the actual concentration of the ions at the electrode surface known as concentration polarization. This is a very important concept. I wish you spend more time to understand this concept, and also I refer you to some standard textbooks to understand this polarization reaction. That means, if you see any variation from the applied voltage, what you are expecting, if it is not there, it means there is some moment of polarization. You give additional potential, but the reaction does not occur. So, what happens to the charge? Only when the charge is passing through, then the reaction will proceed, but you apply the potential, it does not proceed in the reaction, proceed in the correct way. So, it will show you the higher applied potential, but no reaction. So, that is polarization. We will come back to polarization again, but that is a term I wanted to introduce you to. And another concept is over voltage. According to thermodynamic definitions, any half cell is operating irreversibly if appreciable current is flowing. If the current is flowing, the reaction is going in one direction, that means it is operating irreversibly. It is always greater than the corresponding reversible potential as calculated from the Nernst equation, otherwise it cannot go in the reversible direction. The Nernst equation, what you calculate, if the potential is greater than that, the reaction will be proceeding continuously. That means, you are giving energy more than the Nernst equation demands. So, the difference between the actual equilibrium potential and the actual potential is known as over voltage. That means, you are giving extra voltage to the system, and what it means, it is essentially extra driving force we are giving to the system, energy you can call it, the force necessary to cause a reaction to take place at an appreciable rate. Of special importance is the over voltage due to hydrogen ions conversion to hydrogen gas, which would take place at 0 volts if no over voltage is applied. So, this over voltage is another concept very important in our day to day operations. For example, iron 3 plus and zinc 2 plus can be reduced to free metals at a mercury cathode, even though their standard potentials are more negative than standard hydrogen electrode, because we are applying high over voltage of hydrogen ion on mercury, and there is liberation of hydrogen. At a platinum cathode, these ions cannot be reduced from an aqueous solution, as the potential cannot exceed the required rate for hydrogen liberation. So, based on the chemical reactions, what we have described so far is a number of analytical techniques have been developed, either by the measurement of measurement of the voltage, current and resistance, etc. and I would like to explain to you what are these basic analytical techniques that we have been employing. One is potentiometry, that is direct application of the Nernst equation through the measurement of potentials of non-polarizable electrodes under conditions of 0 current. You apply additional voltage, the reaction will proceed. How long it will proceed? Until the applied voltage becomes extra voltage becomes 0. That means, until the reaction attains an equilibrium. So, potentiometry is the direct application of the Nernst equation through the measurement of the potentials of non-polarized electrode and non-equalized under non-equilibrium conditions. So, another technique is voltammetry. Here what we do is a small applied current is impressed across a pair of electrodes, one of which is a non-polarizable reference electrode. That means, you apply any amount of voltage, it won't show you a chemical reaction. So, the electrode is said to be non-polarizable reference. Now, in voltammetry we are using a non-polarizable reference electrode and the other is polarizable, and that is an inert electrode. The current which flows is dependent upon the composition of the electrolyte. So, if the other electrode is a dropping mercury electrode, then it is known as polarography. So, in polarography is another technique in which the voltage or current is measured, in which the one electrode is non-polarizable and another electrode is polarizable. Amperometry is similar to polarography, but both electrodes are not polarizable. Usually current voltage curves are recorded in these studies. Now, there is a small error here, it is actually it is not H capital, it is polarography, and usually current voltage curves are recorded in these studies. So, third is conductivity. You can take two identical electrodes and conductance of the solutions between them is measured. Oscillometry, changes in the conductance and other related properties such as dielectric constants are measured by using high frequency alternating current. And another technique is coulometry, that is use of Faraday's laws of electrolysis to define the quantity of chemical change depending upon the amount of electricity we pass through the solutions. That means, you pass 1 Faraday, 1 coulomb, and then the equivalent quantity of the substance should be deposited. So, electrodeposition techniques are based on coulometry, and chronopotentiometry is recording of transient currents flowing immediately after closing an AC circuit, but before attainment of the equilibrium, that is transient changes as and when they occur before they attain the equilibrium is what we measure in chronopotentiometry. You do not have to really worry about these techniques, because I am not going to teach you all of it. I am going to teach you only polarography and potentiometry. So, other things you can look them up in standard textbooks, but if you understand potentiometry and polarography, you will understand most of the other concepts in other analytical techniques I have described earlier with respect to potentiometry, voltammetry, amperometry, coulometry, conductimetry, and then chronopotentiometry. All these things will become very simple if you understand the potentiometry and polarography. Now, the requirement is most of the concepts of electrochemistry are defined in these two techniques. Therefore, if you understand these two techniques, you would not have any difficulty in understanding other techniques whenever there is a need for you to go for those techniques, or you want to study for, you can study on your own. Now, I want to take you to potentiometry. The potentiometry is a separate science by itself, and according to the Nernst equation, potentials of a reversible electrode permits the calculation of the activity or concentration of the components of a solution. For example, here I am showing you a silver nitrate solution and with a cation here, and another beaker contains ammonium nitrate solution, and then it is connected to a calomel electrode, that is Hg2Cl2, that is electrode of the second kind, mercurous chloride in KCl, and then inert electrode, and you take a wire from the bottom containing mercury, that is Hg2Cl2 plus chloride plus mercury. So, this is a reference electrode. Calomel electrode is one which we use very regularly for most of the reference works, and silver chloride electrode is has got its own other uses, and it is much still simpler to use silver chloride electrode compared to calomel electrode, but commercial versions of calomel electrodes are available. You can easily buy them in the market and use them for your studies. This is one of the reasons why electrochemistry has become so popular, because most of the chemical components cost almost nothing. You can just with a modest investment, you can set up an electrochemical laboratory and do high quality of work. So, coming back to this potentiometry, we can write the equation here in this slide. Basically, what is happening? I have a silver solution, and then there is a salt bridge containing ammonium nitrate and agar, and the one end is dipped in silver nitrate, another end is dipped in ammonium nitrate solution, and which is connected electrically to a calomel electrode, and this silver electrode is here, and both this and minus are connected to a potential source, like a battery or other systems. So, this is the system. Now, I can write an equation like this: EAG, that is potential of silver ion, is nothing but standard electrode potential of the silver ion E naught Ag plus RT by NF Ln oxidized state by reduced state. For example, in this standard, it is a standard form of expression, and silver without charge is metal, that is at the bottom of this equation as the denominator, and silver plus is this thing. And since most of the metals have got activity as 1, we can write E naught EAG is equal to E naught AG plus RT by NF ln AG plus, because ln AG is 1. So, against this we have ESC saturated calomel electrode is connected, and that has got a standard voltage of 0.246 volts. Now, look at it. When we connect both these two, we get some amount of current, electricity, potential. So, the potential of this cell is given by EAG minus ESC. That is, we can write EAG as E naught AG plus RT by NF ln AG plus ESC remains the same. Now, E cell, I can rearrange this equation as log AG plus is equal to E cell minus E naught AG plus ESCE. I am transferring this on the other side, and divided by 2.303 RT by NF. So, that is converted to logarithmic scales. So, by putting the numerals, E cell is 0.400, E naught Ag is 0.799 and this is 0.246, that is calomel electrode, and divided by 2.303 RT by NF, that is standard value is 0.0591. This multiply the when you put all the constants in this, it is a good number to remember, because RT by NF multiplied by 2.303 is 0.0591. So, when you solve this, you get ln log Ag plus is equal to 2.59, or convert it into silver concentration, Ag plus is equal to, you have to take the antilog of this, that would give you 2.57 into 10 raised to minus 3 molar. That means, when you have this cell, and if it shows you the 0.400 volts, at the concentration of silver should be 2.57 into 10 raised to minus 3. Just by measuring the potential, now we are putting all the thermodynamic equations, we are able to calculate how much of silver is there in the solution just by measuring the potential. That is the beauty of potentiometry. You measure the potential, you can straight away calculate the concentrations of silver chloride, silver chloride, both of them you can, but it is actually the concern, what you are measuring is the activity. For our convenience, we are not taking activities into consideration, because most of the solutions what we are dealing with are supposed to be dilute solutions, especially in potentiometry and voltammetry, and activity coefficient is almost taken to be same as 1, that is concentration and activity are almost replaceable in each of these. You will also further note that we always subtract the more negative value from the more positive value. That means, the natural reaction, it should be, the output should be positive, more negative should be subtracted from the more positive, and then 2.303 RT by NF is 0.0591 and PAg is nothing but negative log of Ag. So, if you remember, this is a form of notation, actually third one, negative log, instead of writing negative log of Ag plus, we are simply writing PAg. The significance will become very clear to you very shortly, because when we write H plus, we get pH plus, pH. So, as another example, consider a cell of platinum electrode dipping in 0.1 normal ferrous sulphate with standard calomel electrode. Saturated calomel electrode is as another unit. One is an electrode, platinum electrode dipping in a concentration of, in a solution of ferric and connected to a salt bridge in another system. The salt bridge is connected to saturated calomel electrode, just like what I had shown you in the previous one. Here this is solution, iron solution with a platinum electrode, the remaining part remains the same, the rest of it remains the same. So, if you consider such a cell, potential difference of about 0.395 volts is obtained. You just connect it to SHE and standard electrode battery, and what you will be observing is 0.395 volts. Let us say it is only an example. It is desired to obtain the, you can calculate actually the ferrous which has been converted to ferric. It is a very simple reaction basically. What we write is like this: EMF of ferric to ferrous electrode, that is actually platinum electrode, and the species are ferric to ferrous in contact with each other, is nothing but the standard electrode potential of ferric ferrous with respect to hydrogen electrode, that is available from the table which I had shown you earlier, plus R T by NF ln Fe3 plus by Fe2 plus, that is ferric and ferrous oxidized species divided by the negative species concentrations actually. So, if you measure the E cell actual difference when connected, you can write as E Fe3 plus by Fe2 plus R T by NF ln Fe3 plus by Fe2 plus. This is actually E cell. You can rearrange these equations, this equation actually R log of Fe3 plus by Fe2 plus, I am retaining on the left hand side, E cell on the right hand side actually, E cell minus this I am transferring this side, that is minus E naught Fe3 plus etcetera, and then ESC standard electrode calomel electrode should come there, and then divided by RT by NF, that is 0.0591 volts. So, the voltage what you are getting is minus 2.20, that is not the voltage actually, it is minus 2 point, this is the minus 2.20 is the number what you are getting by reorganizing this. This tells you that the ferric taking antilog of this ferric to ferrous would be nothing but 6.3 into 10 raised to minus 3. Take the antilog of this, that means 0.63%. That means 0.63% of the ferric ferrous solution has been converted in a given solution. If you connect 0.1 molar ferrous sulphate with standard calomel electrode, and you are getting 0.395 volts. Just by knowing the value of 0.395 volts, we are able to calculate what is the ferric concentration and what is the ferrous concentration, whether it is pure ferric or not so pure ferric. So, it is a very useful entity which can which tells you that whether a given system is in what condition, that is if the subject, if the more of ferric and less of ferrous is there, you would get ratios nearer to 1, and if more of ferrous and less of ferric is there, that means if the chemical is impure, you would get higher ratio. So, just by knowing the EMF, you can calculate the actual concentrations. Similarly, consider another system in which I have two similar electrodes, but dipped in solutions of different concentrations. You can take a look at this. If two identical electrodes are placed in solution differing only in concentrations, but connected by a salt bridge, the potential between the two electrodes is related to the ratio of the two concentrations. Consider for example, this cell, here I have put silver electrode in a solution of silver chloride and connected with a chloride solution of having concentration x, and that is one half cell. The other half cell is chloride solution of a standard chloride solution having same silver chloride and silver electrode, AgCl electrode we call this. So, actually this is known as junction potential. Junction, I have silver chloride electrode dipped in a solution of chloride solution of unknown x, but it is connected with a salt bridge to another solution containing a known amount of chloride, that is standard, but a another silver chloride electrode has been dipped in that. So, we can look at the system like this. Suppose the standard is 0.100 m molar. Its a single electrode potential is given by Nernst equation, that is E, E standard is equal to 0.222 volts minus 0.059 volts log of the oxide species, that is concentration, log of the concentration of the oxide species, that is 0.100 m here. Reduced species is 1 because it is metal, and that value is 0.281 volts. If the unknown is more concentrated, let us say 0.1500 molar, here it is 0.1000, here it is 0.1500. Then E x unknown I can write like this, 0.222 volts minus 0.059 volt, 591, same equation I am rewriting as on the top, and log of instead of 0.100 I am going to write 0.1500. Since the electrodes are same, since the silver chloride and silver on the left and right are same, they cannot contribute to any difference in the voltage what you observe, but the only difference should come from the concentration of the standard and the unknown. So, you can calculate, actually E cell you can measure by connecting the connecting the solutions to a source of electricity. What you would see is 0.1 volt flowing through, and that is nothing but E standard minus E x standard, E x unknown. Now, imagine I have a solution of 0.68 molar, then I can write a similar equation, and E cell is equal to 0.010 volt. Just go back, for 0.1 and 0.15 you are getting 0.01 volt, and even when the unknown is changed to 0.680, you are still getting 0.010 volt. So, any measured potential is open to ambiguous interpretations, which may be avoided by noting that the interpretation corresponds to more positive of the two. So, the concentration cell, this is a concentration cell, it provides us a convenient tool for the measurement of pH. How, we will see later. Thank you.